to share the slides? Is it Mansi?
Yes, so welcome, sir, for another session with
Thank
you on EMT.
Thank you very much.
Yes, and today you're going to enlighten us further. And I request my co-organizing team, Dr. Parul or Dr. Mansi, to kindly start sharing the screen. Sir, it would take a delay of a minute or so. And then, yes, it's visible now. Please use a bigger screen option so that it is visible to the students. Can you make it larger? Yeah, this one. Exactly. So you either use the plus sign or make it to 100%.
Is it okay, ma'am?
No, the slide is being cut, as you can see for yourself. So you have to enlarge your screen. Yeah. Okay, and maybe you can shut off your right side where some commands are written, like export PDF, edit PDF, etc. Yeah, view the file in the read mode would be a better option. Yes, I think it is. I think it is clearly visible right now. So I request, sir, please continue.
Yeah.
With,
Thank you, ma'am. I would. Shall I make a beginning now?
Yes, sir. This is sir. Please start your
okay.
lecture. This is your first slide, and yes, please continue.
Yeah.
The next slide, Dr. Parul, please go to the next slide now. So, sir is going to speak on EM fields in homogeneous unbounded media, local response of medium to EM fields.
Yeah, but before I speak about this topic, this is slightly advanced, though it is in the syllabus. Though of course it's in the syllabus. I would like to ask a few questions from the students. I don't think students mind making a beginning with some simple questions, just to test whether, because they had a good lessons from Dr. Rachna Kumar, and probably they are now well aware of certain basics of electromagnetics. So my first question is, how Maxwell fixed Ampere's law? This is my first question. Although there is no slide for this, I just asking out of the, well, it is a very well-known question and it's come in the university as well. So students ought to know this.
I think somebody has answered. Just have a look.
Yeah, someone said the concept of displacement current. Well, that is true to a certain degree, but if we would like to go to the basics, my answer would be, this was continuity of flow of charge. Very good, very good. A continuity equation for of flow of charge, or the charge conservation, was introduced to fix the Ampere's law by Maxwell. To discuss it in simple terms, continuity equation is del dot J. J is current density, is negative of del rho del T, where rho is the charge density. And using the Maxwell's first law, which I'm sure everybody knows, divergence of electric field is charge density upon epsilon naught. So using this equation, the del rho del T could be written as minus del dot epsilon naught d dt. So ultimately one gets del dot mu naught epsilon naught d dt plus mu naught J equals 0. So if one writes curl of B as mu naught J plus mu naught epsilon naught d dt. Left hand side is curl of B. Take divergence. Divergence of curl of any vector field is 0. And we just now have proved from the charge conservation that uh, mu naught epsilon naught d dt plus mu naught J is 0. So we get 0 equals 0, which is perfect. So that's how with the help of equation of continuity or charge conservation, Maxwell fixed Ampere's law. My next question would be, again, a simple one. One is familiar with Maxwell's equation, I assume. They are coupled equations. How many of them are there? How many? Well, it is neither 4. People are saying 4 and 2. It is neither 4 nor 2. It is actually 8. I don't think, or if you need explanation, curl of E, of course, has minus del B del T, which is Faraday-Newman law of electromagnetic induction. And next one is the Maxwell's fixing of Ampere's law, which is uh, curl of B equal mu naught J plus mu naught epsilon naught d dt. So we have two equations, curl of E equal minus dB dt and curl of B equal mu naught J plus mu naught epsilon naught d dt. These are vectors. In three-dimensional space, there are in total 6 equations. And apart from them, you have the Gauss's law in electrostatics. Del dot E equal rho upon epsilon naught, one equation, and del dot B equals 0, Gauss's law of magnetostatics. So in total, there are 8 equations. And these 8 equations can be easily reduced to 2 equations. Someone has given answer 2 equations. Well, they could be reduced to 2 coupled second order differential equations in terms of scalar and vector potential. In terms of scalar and vector potential. Now, some condition fixing is needed for this task. Can anyone tell me what are these conditions called? What are these conditions called? Exactly. Samiran Banerjee is saying Lorentz condition. Very good. Lorentz gauge condition. Lorentz gauge conditions are obtainable from the fact that E is actually minus grad phi minus del A del T and we have this is a definition of E, and then we have divergence of A equal mu naught epsilon naught del phi del T equals 0, which is our Lorentz gauge condition. And well, then I ask a theoretical question, which of course is somewhat perplexing. Suppose we all know that quantum of electromagnetic field is a photon. I'm sure our students know this now. So does a photon gain instantaneously the speed of light, or they do accelerate from 0? My question is, does a photon being the quantum of electromagnetic wave, when the electromagnetic field is quantized, we get quantum of electromagnetic field as photon. So does a photon instantaneously gain the speed of light, which is c equals 1 upon square root of mu naught epsilon naught, or do they accelerate from zero? What is the answer? Accelerated. And someone saying instantaneous. Instantaneously. Well, it is neither of the two. I'm sorry. Neither instantaneously nor accelerated. As I look at it, photon is, of course, a manifestly quantum object to which our classical concept like accelerations, etc., do not naively apply. But forget photon at the moment. Let's take a step back. We have plain electromagnetism. Vacuum speed of light in this context refers to the propagation of plane wave in the electromagnetic field far from any charges, because only when charges are very far, the wave will have a plane wave front. That is known to everybody. If the charges are quite nearby, near charges will give rise to spherical wave front. So plane wave solution, which we have been habituated, I'm sure my students also have applied plane wave solution in one problem or the other. The solution for near charges no longer apply. I'm sure all of us agree on that. So when we solve Maxwell's equation for near charges, there would be no plane waves propagating at the vacuum speed, which is 1 upon square root of mu naught epsilon naught. There will be complicated solutions, which will be a combination actually of plane waves and spherical waves in accordance with Huygens principle. And propagation speed will be less than speed of light. In fact, in the presence of charges, the photon propagator, it does not behave like a particle massless traveling with speed c. Photon behaves as though it has an effective mass, and it is carrying energy, momentum, etc. And in presence of mass or charges, it travels slower than speed of light in vacuum. So transition from the vicinity of charges to the empty space is smooth. Therefore, the answer to the question that I have raised is very difficult question to answer. Reason being, photon cannot be, as I said, considered as a classical object. It is, as I mentioned in the beginning, is manifestly quantum one. So with these questions, now we go to the slides, which is projected. So here we are discussing unbounded medium and what would be the EM fields in this unbounded media, and what would be the local response of medium to such EM fields. Now, the concept of EM field is introduced to describe how charges interact with each other. Every charge generates its EM field. Charge in motion, of course, generates its EM field. I am repeatedly saying EM field. This means it is neither electric field nor magnetic field. In fact, as we all know, that EM field corresponds to a second rank antisymmetric restless field strength tensor. Anyway, I'm not going to the covariant representation of electromagnetic field, but let us remember that when I say EM field, I don't have neither electric or magnetic field in mind. We are in fact looking at a tensorial object, which is the tensor, the field is a tensor of second rank, and it is anti-symmetric and traceless. Now, anyway, coming to the fact that every charges generate EM field, in the case of multiple charges, overall field will be given by the sum of corresponding fields generated by every charge. As a result, full EM field description will require as many as 10 to the power 30 charges per meter cube. That is the number of free electrons which are available, say, in a metal, in 1 meter cube of metal. It is a very troublesome and complicated procedure. To simplify this, we ignore all fluctuations which appear at atomic scale. We had thought of a length which corresponds to, in fact, a volume. Cube of that corresponds to a volume. A length A macro, and A macro is much greater than the lattice constant. So A macro cube volume is much greater than the volume corresponding to a lattice constant, and we ignore all fluctuations in field at this scale, and that ignoring fluctuations, meaning averaging over a volume which is much larger than a volume corresponding to lattice constant. So within this approach, we have the usual equations, del cross E minus dB dt, del cross B is mu naught epsilon naught d dt j. Two divergence relations are written down, del dot E and del dot B. Now total current density will be in a medium due to polarization and due to extraneous factor. Now polarization, then current density over total volume would be zero. I don't need to explain this to anybody, because how dielectric or molecular polarization takes place, everyone is aware of it. Current density integrated over entire volume is, of course, extraneous current density will not be zero. So with this, we go to the next slide. Next slide, please. Next slide, which is 3 naturally, or no, as per numbering, it should be 2.
Next. Yes, sir, I am changing. Yes.
Yeah, no, not yet. Yeah, this is it. We have Maxwell's equation here in terms of polarization and magnetization. Polarization vector, magnetization vector we are familiar with. We have electric displacement vector equal in free space epsilon naught electric field, but in dielectric epsilon naught E plus polarization vector, and magnetizing field vector is 1 by mu naught, which is permeability of free space. Permeability, of course, is power of conduction of magnetic lines of force for a medium. So 1 by mu naught B minus M. M is the magnetization vector. So this allows us to write our Maxwell's equation in terms of the electric displacement vector and the B, the induction. So you have, of course, magnetizing field H. So we have curl H equal del T plus J external, and curl E equal minus dV dt, and two divergence relations. Divergence D equal rho external divergence B equals 0. Furthermore, polarization, of course, the current density of polarization is divergence of rather current, not current density, I am so sorry. Charge density of polarization is given as negative of divergence of polarization vector. And current density of polarization.
Can you please shut off your video? There is some voice
There is
problem.
what problem?
Voice problem. Can you please shut off your video?
Okay, okay, I would.
Thank you.
Okay,
Thank you.
so the charge density of polarization is negative of divergence of polarization vector, and current density of polarization is the time derivative of polarization vector plus curl of magnetization. So we want here discussing this unbounded medium, propagation of EM wave and electromagnetic field in this medium. We want some results where medium's boundary is much larger than the characteristic length scale of the EM wave confinement. And the EM wave confinement is given by the bulk eigenwave propagation length. The point to note here, because I have been in the past also in my lessons on classical mechanics, emphasizing on cause and effect. So I would like here to emphasize that charge density and current density are the sources. They are the cause, and electric field and magnetic field are the effects. And we, as we know, I have spoken about it already, we all are bound by a causal chain. So here also we see that we must remember that current density and charge density are cause, and due to these causes, the fields arise. E and B are effects. With this, we go to the next slide. Next slide is local response approximation. Now, in local response, what do I mean by this approximation for our non-uniform medium? Our task is finally, as we have in the syllabus of BU, and which is a favorite question of examiner, derivation of Fresnel equation, etc., wherein we consider piecewise continuous medium. So, what exactly is the local approximation for non-uniform media? We need to understand. We start with the fact that we have assumed that all fluctuations which are less than the lattice constant or volume corresponding to lattice constant, they have been ignored. In fact, the averaging of fluctuations have been made over a volume A macro cube. So all microscopic inhomogeneities appearing at a scale below A macro are suppressed while we do the averaging. I'm sure students understand this because they have at the school level calculated, let's say you have time varying current, alternating current, they have calculated average current, they have calculated root mean square current, averaging over a time equal the entire time period, and the fluctuations ultimately, for example, one if calculates root mean square current, it becomes the peak current divided by root 2. The fluctuations in the current over time smaller than one periodic time, it does not appear in that expression. So this is what I am writing here, that all microscopic inhomogeneities appearing at a scale below a macro are to be suppressed, and inhomogeneities at a scale above a macro, however, they do not get eliminated. Thus, for, let's say, very generalized, anisotropic, non-uniform medium, it is imperative that the cause and effect, rho, J, E, B, these are cause and effect, they should be written in local approximation. Local approximation is response depending on at what position in space one is. So I have written a particular response function, though formidable to look at, but it is very simple. It is nothing but Ohm's law. Supposing one applies electric field E at a point R, what does one get? One gets as a response, the response function is the current density. So what one has written simply is JITR integrated over time t dash, where t dash is less than a certain time t, starting from minus infinity. So sigma ij, you see, and for an isotropic medium, all quantities are going to be tensor. That in different directions, quantities would be different. I'm sure this has already been taught to the student. So our conductivity tensor is sigma ij t dash r e. So this is nothing but generalized form of Ohm's law only, describing the response of a medium to electric field. Now, sometimes from real space or time, it is convenient to go over frequency and wave vector, or frequency and R space by taking Fourier transform. I'm sure in mathematical physics, everyone has studied what Fourier transform is: frequency time transform, real space and momentum space transform. So in a uniform media, we make a non-local approximation. Our dependence is not there on any quantity, so we take a omega k transform, frequency wave vector transform. On the other hand, in a non-uniform medium, it is imperative that we take frequency and real space transform. So our equation or Ohm's law reduces to Ji omega r equal sigma ij, which is conductivity tensor omega r, eij omega r. These are the Fourier transforms of our current density, complex conductivity, and electric field. So sigma ij, as I have written down, is the tensor of complex conductivity, and electric field, electric displacement vector will also be dependent on real space, and this is how the definition will appear. And the permittivity in an isotropic medium will also be a tensor. I'm sure everybody, because it is in the syllabus, everybody had studied propagation of EM wave in an isotropic medium, where permittivity becomes a tensor, and it is given It is related to conductivity tensor in this fashion. So a local response meaning mathematically it is simply, it amounts to taking Fourier transform of all equations to omega r space. Omega is frequency, r is real space. We don't go to momentum space. Momentum space we only allowed to go to when medium is uniform, and under that we are since property is all over at all points same, so one can make non-locality transform. Now in case one has magnetically inactive isotropic media, the equations for electric displacement and magnetic induction, etc., will be given by d omega r equal epsilon naught epsilon omega r e omega r, and b omega r equal mu naught h omega r, and so on. So you see, when I have a non-uniform medium and an isotropic as well quantities, the Fourier transforms that we take over omega and r, frequency and real space. However, when we have uniform media, we make non-locality transform and we take Fourier transform over omega k space. The important point is, for an isotropic medium, quantities like conductivity, the permittivity, etc., are tensors of second rank, whereas for isotropic media, they are simply scalar complex quantities. So, if I am to solve a problem of a non-uniform medium, I need to specify ab initio what should be the profile of our permittivity. This needs to be specified. Like shortly, we are going to solve the, I'm going to obtain Fresnel equation, where we shall consider actually two media which are both uniform but separated by an interface. In one medium, permittivity is epsilon 1 and throughout constant, and in another medium, permittivity is epsilon 2. And accordingly, the dielectric constants, which one, I'm sure everyone knows, is square root of permittivity, is going to be N1 in one medium, N2 in other medium, and there is a separation between the two media. There is this interface. With this, we go to Maxwell's equation and how they look like in local approximation. This is definitely a difficult slightly difficult mathematics. I have not gone to omega k space. I have gone to omega r space because I am making local approximation. But at this juncture, okay, please go to the next slide. Please go to the next slide. In fact, this also is over. Please go to the next slide. 4. Yeah. True. That is what. Yeah. Let me at this juncture ask a question. Why do we need to go to if I have almost all differential equations in all problems involve real space and time, real time. Why do I need to why do I need to consider Fourier transforms? Either in omega r space, as in the case of local approximation, or omega k space, as in the case of non-local transformation. Why do I need to take Fourier transform? Can one tell me? Can anyone tell me? No, the answer is mathematical consistency. No, no. Samiran Banerjee is saying mathematical consistency and emphatically no. Please find out what it could be. Easier mathematical approach, Charubala, to get time independency. No, time independency also. How can you get? How can you extricate yourself from time independence? We all are living in space time, in a certain fabric of space time. So the answer is, I'm sure people have done the Fourier transform, so but have not probably realized, or I don't know, whatever the case is. You see, most of the equations in physics are differential equations. And these equations are coupled differential equations and system of coupled differential equations, so to say, like Maxwell's equation, as I pointed out, has actually 8 equations. They are coupled. Highly coupled differential equation or a system of differential equation is Einstein equation in general relativity. So every equations are a system of coupled differential equations, difficult to solve. Difficult to solve. So what does one do? When one takes Fourier transform or Laplace transform, as the case may be, such differential equations are transformed to a system of algebraic equations. Now, a system of algebraic equations are definitely easy to solve. So, like here, we are interested in non-uniform medium electric magnetic field, solutions for electric and magnetic field in local approximation. So these are our quantities to be obtained. And as we can see that we have obtained, say for any field, we have applied a particular theorem, Helmholtz theorem in vector analysis. One can see that where fields could be uniquely decomposed into longitudinal and transverse component with curl of longitudinal component 0, divergence of transverse component also 0, and the decomposition leads to the Maxwell's equation in local approximation for longitudinal part as a certain expression, as one can see, and for transverse part there is ht equal omega r minus I omega epsilon omega r epsilon naught et plus jt external omega r. So what is happening? The moment you take Fourier transform, your complicated coupled differential equations got reduced to complex algebraic equations which could be easily solved may not be easily, but much more easily than a differential equation. And once solved, one will get the Fourier transform. One would take inverse Fourier transform to get back the quantities sought for. Is my explanation clear? Is my explanation clear? Okay, very good. Oh, very good. So it is a more of a matter of convenience and expediency. Differential equations are difficult to handle. You may reduce them into algebraic equations, system of algebraic equations, and solve the system. And after the solutions been obtained, there would be solutions for Fourier transforms. Take inverse Fourier transform, you get back the quantity which you want. So this procedure is also, I'm sure, is applied in quantum mechanics. I am not able to resist the temptation. Schrodinger equation is, of course, a differential equation which involves first derivative of time and second derivative of space. So it is a differential equation. We all know this, time-dependent Schrodinger equation. Now, if I have uniform medium, I can I can take Fourier transform of, say we have particle in an appropriate potential, we have taken appropriate Fourier transform of Schrodinger equation. Will I still get a differential equation, or what kind of equation I get in terms of wave vector? In terms of, say, time independent, you talk about. In terms of wave vector, what do I get? Because assume uniform medium, so you are taking omega k transform, k wave vector, right? And forget time dependence for the moment. Take time independent Schrodinger equation. So you are getting equation in terms of wave vector. What kind of equation is this? Answer. Has anyone not ever seen a Schrodinger equation of a particle in some kind of potential? But expressed in terms of wave vector. No one has seen so far. You have seen Surendra Kumar. So you tell me, how does equation look like? No idea. So please check this equation once. It is a good exercise to, because you want to have a, no, not linear, not Soumyaram Banerjee, it is not linear. It becomes integral equation. Integral equation. I'm sure all of you, or may have heard, but not yet had any with integral equation. So it becomes integral equation, and the potential in real space, in place of that, you have a convolution. Convolution in the case of Fourier transform or Laplace transform, one has studied. So one has convolution of potential involved in the integral equation, which is our Schrodinger equation in momentum space. So linear space, so Schrodinger equation is a differential equation, whereas momentum space Schrodinger equation is an integral equation involving convolution of the potential. Anyway, that was slight digression. But a point has to be made clear. What is the need to go to the Fourier transform? Now, Maxwell's equation in the local approximation, in general, the solution of fields, transverse electric or magnetic field, could be sought as a sum of two polarization called transverse electric S wave, it has named S wave polarization, transverse magnetic TM P wave polarization. So with this we go to the next slide. Please go to the next slide.
Sir, is it okay?
In the next slide is T and TM polarization. Next one.
Next. Okay, sir.
T and TM polarization is written no, at the top. It is T and TM polarization.
Sir, is it okay?
Yes. It is all right. And you have del square defined anyway. So in T polarization, I've written down after solving, one gets Maxwell equations in this form. I don't need to, because I have defined every quantity out here. K0 square is omega square upon C square. And you may notice that for electric field, you have a wave-like solution. But not for magnetic field. In TM polarization, Maxwell's equation are reduced to equation for magnetic field HT, and HT will have a very complicated equation. And if for electric field also, you have a complicated result. In both cases, you have to provide, give your student, give yourself a profile for epsilon, profile for dielectric constant, as I am shortly going to give a profile for dielectric constant, which is the simplest possible profile to uniform media separated by an interface. So with this, we go to the next slide, and this is from where the derivation of Fresnel. Please go to the next slide. No. You are right. Piecewise homogeneous media and Fresnel equation. Yeah, this is the next slide. Okay. So we consider the most frequent, and I have stated my problem. I consider most frequent and fundamental macroscopic inhomogeneity, which is an interface between two media. We assume every medium per se is, when standalone, is isotropic and homogeneous. And in there is an interface separating the two media, and we are very far away from the interface, and every medium, two media which are under consideration, can be described by bulk permittivities epsilon 1 and 2, dependent on omega frequency only, not on R. Reason is that it is a standalone media, each medium is uniform, so not dependent on R. However, close to interface, which we never go, it smoothly changes from E1 omega to E2 omega within a few transition layer. So this is our problem, and for this problem I am to derive the Fresnel equations, Please go to the next slide where we have shown T mode. Yeah, T mode, that is S polarization. In fact, E and B has got displaced from their position in the figure. E is the electric field, which is, we have a surface separating two media. Their refractive indices are N1 and N2. One can see that. And let us suppose N is N2 upon N1, and I have an electromagnetic wave. Basically, here I am denoting field by E. So this is the field incident, and part of it gets reflected, which is ER, part of it gets transmitted. Theta is the angle of incidence and theta r angle of reflection. Electric, this T mode, transverse electric mode, electric field is perpendicular to the direction of E, and magnetic field is in the same, in the so-called horizontal plane. And R we shall calculate, T also we calculate. These are our reflection and transmission coefficient. R will be simply amplitude ER upon E, and T transmission coefficient will be amplitude ET upon E. This is a diagram of T mode, and I have shown also a diagram of TM mode, more or less same diagram. We have now magnetic field perpendicular to direction of E, and electric field in the same plane. Theta and theta r are the angles of incidence and reflection, and theta t the refraction angle or transmission, and N1, N2 are the refractive indices, and N I take subsequently as N2 upon N1. My task basically, as I again have I have emphasized, is to calculate reflection and transmission coefficient. This is TM mode. You are sorry, you are still showing TE mode. I'm sorry, I did not ask you to go to TM mode. Yeah, TM mode. Same diagram as I said, only magnetic field now perpendicular, but this gives, as we have seen, a lot of difference in the equation. And theta are the angle of incidence and reflection. Theta t, refraction, angle of refraction. N1, N2 are the refractive indices of the media. N is quantity we shall introduce, which is N2 upon N1. R reflection coefficient, T transmission coefficient. With this, please go to the next slide. Yeah, reflection and transmission coefficients we calculate now. I have not calculated in this slide. I have simply shown the results that we shall get after calculation. RT I have defined as I already told you, ER upon E, which will be cos theta square root of n square sine theta cos theta n square minus sine square theta and all that stuff. RTM will be what is written there. I don't need to repeat. And T transverse mode ET upon E 2 cos theta upon cos theta plus square root of this quantity n square sine square theta. TTM will be ET 2n cos theta n square cos theta square root of n square sine theta. We assume that plane wave far away, the charges far away, so no complicated description. We have plane wave front, incident wave front, amplitude EOI, exponential I, KI. KI is the incident wave vector. KI dot r minus omega I t. Omega I is the incident frequency of the reflected beam. ER is amplitude term, EOR, E0R rather, exponential I, kr reflected wave vector dot r omega rt, and for transmitted ET is EOT exponential I kt dot r minus omega t. So in this slide, I have summarized the results that we shall obtain. And we have also written down that our incident beam, reflected beam, transmitted beam, they are all assumed to be some kind of plane wave. You may wonder what is the fun in getting these coefficients? What will one do? Well, with these coefficients, one can explain external, internal, total internal reflection, etc. One can explain Brewster's law. Was all optics related phenomena could be explained with the help of these fundamental relations. Now, to get to derive this relation, I have taken for all time t and for all boundary points r on the interface, the tangential components should be, I emphasize that tangential components must be equal on both sides of the interface. This is like a ball, a cannonball striking a wall or something, getting reflected back at a certain angle, then momenta in the tangential direction will always will remain same. So that kind of condition I am imposing. So with the imposition of this condition, please go to the next slide where I have my handwritten expressions. Yeah. So we have n caret is a normal vector, unit normal vector. We have, as we stated, that the tangential components for all time, all boundary points on the interface, tangential components must be equal on both sides. Recalling that, or translating that in mathematical terms, it means n cross ei, n cross er should be equal n cross et, and to that, if I substitute expressions which we assume, the plane wave description that we assumed for electric field, we put in that description. So we have n cross EOI exponential I KRT omega I plus n cross EOR exponential, all that. So we assume now that the wave amplitudes are constant. Now, if wave amplitudes are to be constant, the only way this can be true over the entire interface, at all points on the interface, at all r in the interface, and for all time t, this could be only true if the phase term or phase matching takes place. That phase term is k dot r minus omega t. So phase matching gives me ki dot r omega it, kr dot r omega rt, ktr dot r minus omega t. So I have so far put in two requirements for all time or for all boundary points are on the interface, our tangential component, which anyway should be same, must be equal on both sides of the interface, and we have put in the second condition that wave amplitudes are constant. With this, I go to the next slide. Please go to the next slide. Here, yeah, right. So here we have
Sir, is it all right or previous one?
no, it should be previous one.
Okay.
Yeah, that's what it is. Previous one. Yeah, it should be this. Okay.
Okay.
So at R equals 0, our phase matching result gives obviously omega I equal omega R equal omega T. Very easy to see, everyone can see that. No, so frequency doesn't change at the boundary, which is very well known. At equal 0, the result is K dot R, K for I as well as R as well as T should be constant. So this means that what is this equation for? That means for a plane perpendicular to K, the wave vector incident, wave vector reflected, wave vector transmitted, the equation refers to a plane perpendicular to the incident, reflected, transmitted wave vector as well as R vector. R vector is any vector, any point, position vector of any point on the boundary. And if that is that, then Ki, Kr, Kt wave vectors are all coplanar in the plane of incidence. Now at t equals 0, since ki dot r, k dot, kr dot r from phase matching, kt dot r is constant, considering the relation between the parameters of the incident reflection beam, we have obtained ki dot r equal k dot r. And this finally leads to, please go to the next slide. This finally leads to, KIR sine theta equal KR sine theta I, KIR sine theta I equal KRR sine theta R, and incident and reflected being in the same medium, Ki being equal Kr, we just now have proved, equal Ni omega by C. So it implies sine theta equal sine theta I equal sine theta R, which is our law of reflection. And to get this Snell's law of refraction, we consider the relation for incident and transmitted beam, where we have Ki dot R equal Kt dot R equal KIR sine theta I, which is of course one would say, why sine theta? Why should not there be cos theta? I think it could be figured out from the figures that I have given in earlier slide. So I don't need to go into that. I think so. KTR are sine theta t, but the incident and transmitted beams are in different media. So they have Ni and Nt as the refractive indices. So Ki will be Ni omega by C, Kd will be Nt omega by C, which leads us to law of refraction. Ni sine theta I equal Nt sine theta t, Snell's law. So we see that boundary condition, following the boundary conditions from our Maxwell's equation, the boundary condition at the interface, we have been not exactly boundary condition, we have imposed, in fact, two conditions, that at there should be phase matching, and also there should be for all time and t, for all boundary points on the interface, tangential component must be equal on both sides of the interface. So if you wish, you can call it as boundary condition anyway. So we see that we are able to derive law of reflection and law of refraction. Furthermore, our following our boundary condition at the interface for transverse electric case, that is S-wave polarization. Please go to the next slide. No, not this. The one before it. Not exactly. Next slide is where you have, no, not this. No. This one, this one, this one. No, not this one. Sorry, the previous one, previous one.
This one, sir.
No, no, not this one. You showed just now.
This one, sir. Or this one.
This one, yeah,
Okay.
exactly. This one.
Okay.
This is our next slide.
Okay.
We have in the transverse,
Sir, the slide, so
yeah.
the slide numbers are same as what you designated, so you can identify them by the slide.
Acha, acha, okay, okay. So
Slide
I
numbers
would
have
now,
not changed at all.
okay. So this is 13th number slide. So we have EI plus ER equal ET, and with these boundary conditions giving me BI cos theta I minus BR cos theta BT cos theta T in transverse electric field case. The above conditions in fact imply that tangential components of both electric and magnetic fields are equal on both sides of the interface. And we have also assumed non-magnetic medium. That means the permeability of incident medium, medium of incidence, and which is same as medium of reflection, and medium where transmitted rays go. All of them are a non-magnetic medium. So therefore, mu I, mu t is mu 0. And for Tn case, on the other hand, we have EI cos theta I plus ER cos theta R equal ET cos theta T, and minus BI plus BR equal minus BT. And we recall that E equal B propagation speed in a medium, which is C by NB. Students have seen it. So B is NE by C. So for T mode, I can write down E plus ER equal ET and NE EI cos theta I, and minus no, I have gone over to I ke badle. In place of I am writing now N1. Sorry, I should have stuck to the same notation. But anyway, nothing happens. In the diagram, I have shown the medium from which the light is incident is has refractive index Ni or N1, and medium where the light goes after transmission has refractive index N2, which we have been calling as NT. Anyway, so I have written down EI plus ER equal ET, and N1 EI cos theta I, N1 ER cos theta are equal N2 ET cos theta T for transverse T mode. And for TM mode, we have EI cos theta I, ER cos theta R equal ET cos theta T, and minus. This is simply those equations which we have at the top of the slide and on the middle of the slides. They have been written down in terms of the N1 and N2, sorry, N1 and N2. So we have minus N1 EI minus N1 ER equal minus N2 ET. So we have two sets of equations now. With this, we go to the 14th slide. 14th slide. Okay. So in the 14th slide, eliminating ET from each set of equation and solving, it is algebraic equation. So there is, I need not make, or one need not make a fuss about it. So eliminating ET from each set of equation and solving for reflection coefficient, one gets RT, which is ER upon EI equal, as I have earlier noted in my summary of results right at the beginning, is cos theta I minus N cos theta T and all that. So RTM also written as ER upon EI for transverse mode. Or, the first one was for transverse electric mode, second one was for transverse magnetic mode, and for transverse magnetic mode you have slightly different result. And then I have used Snell's law to write RT and TT. For Snell's law gives me sine theta equal m sine theta t. So n cos theta t will be, this is trivial, square root of n square minus sine square theta I. And substituting, say in a similar fashion, I obtain RT equal EI and also TT equal to cos theta I whole divided by cos theta I plus square root of n square minus sine square theta I. So what one sees is that in the T case you have EI plus ER equal ET, which could be written in terms of the transmission and reflection coefficient RT equal, which are written at the top strip, TT equal 1 plus RT. Transmission coefficient for transverse electric field or S wave polarization is equal 1 plus reflection coefficient for S wave polarization, and n times transmission coefficient for TM is called P wave polarization. So n times transmission coefficient for P wave polarization is equal 1 minus reflection coefficient for P wave polarization. These are within a bubble. I have noted that these are nothing but the boundary conditions EI plus ER equal ET, as in the T case, and minus BI plus BR equal minus BT, as in the TM case. So we have been therefore imposing two very intuitive, beautiful conditions, and of course using Snell's law, we have been able to obtain the transmission and reflection coefficients for the S wave polarization and P wave polarization. So with this, we now go to the next slide, which is number 15. In the number 15, my aim is to, actually I've shown a diagram, very handwritten diagram, very crude one. I have calculated reflection and transmission coefficient for S wave and P wave polarization, but what would be the appearance of these coefficients in terms of power? Therefore, I have considered a beam incident at angle theta I with, let's say, cross-sectional area, a beam cross-sectional area is AI, getting reflected from the interface, beam cross-sectional area is 80, uh, and oh, I'm sorry, it should have been AR. I'm sorry, AR. Please make a correction mentally. AT should be AR at an angle theta R, and AR below transmission part. For transmission part, the refraction angle theta T and area is, say, AT. I believe uh, since we are here power or intensity, we are now going over 2. So intensity is defined as the energy incident over unit area, per unit time in the direction of propagation. So we need to consider area. So we have considered beam area, cross-sectional areas as AI, AR and AT. With this, we go to the calculation part in the next slide. So it is 16th number slide. Here the quantities R and T, which I have calculated so far, are the electric field amplitudes. Suppose capital R and capital T are the ratios of the reflected and transmitted powers, respectively. So R and T will be defined as PR upon PI, PT upon PI, where the symbols are self-explanatory. PI is incident power and PR and PT are reflected and transmitted power. So in terms of product of irradiance, meaning intensity, and area, the incident power will be obviously II, incident intensity, area AI, reflected power IR, AR, transmitted power IT, AT. No big deal, very easy to understand. So we go to now the next slide, which is slide number 17. We calculate now the capital R and capital T, they are called reflectance and transmittance. So from conservation of energy, obviously IIAI, this is the incident energy, and through reflection and refraction at the interface, no energy depletion or no energy creation occur. So conservation of energy implies that EIAI equal IRAR ITAT, and AI actually in terms of because this is slanting area, so you have IA cos theta I equal IRA cos theta R ITA cos theta T, which gives me II cos theta I equal IR cos theta R plus IT cos theta T. But incident intensity, I'm sure all of us are familiar with this expression, half m epsilon naught c propagation the speed E naught square, which is the square of the amplitude, intensity proportional to square of the amplitude. This kind of expression we have used very often. So we have just put in this expression for intensity with N1 and N2, N1 for II, also N1 for IR, but for I2, N2, we put all this and make a slight manipulation and we ultimately apply our previous result to get R plus T equal 1, where capital R is defined as E0 R square, E0 I square, which means reflectance is simply small r square. Transmittance, however, since there is change in medium, so n factor will come in definitely. So we have n cos theta I, cos theta t, cos theta I, E0 t square, E0 I square, which gives me n cos theta I, theta t upon cos theta I t square. So transmittance also we have obtained. So this is the derivation of Fresnel equation, and which is an application of a propagation of EM wave in a non-uniform medium. Now I would put a question. Please go to the next slide. Again, a fundamental question. How one would create EM wave in a particular simple geometry? So I take the simplest possible geometry, in fact, a planar geometry, which is charged. So we know if sigma is the surface density of charge, applying Gauss's law and all that, we have done it at school level. E0 is sigma upon 2 epsilon naught. So with this planar charge, how do we show that we can create EM waves? What exactly, how are, in fact, how do you, or let me put the question differently. How do you create, let's say, transverse wave in a stretched string? Yeah, Swaminathan Banerjee is saying setting the line charge to SHM. I want to, in fact, go a bit deeper. That is why I have posed this question in different language, in a different, and a context also is different. That suppose you have a stretched string and you want to generate, like in sonometer, you want to generate a transverse wave in the stretched string. So how do you go about it? You create a perturbation in the string either by plucking it or by bowing it or by striking it, and this disturbance will propagate through the length. Disturbance will be at right angles to the propagation, so the wave will be transverse, and it will propagate through the string. And maybe if there is some end, rigid fixed end, from there reflected wave will be generated and leading us to stationary wave, node antinode formation. So that is the story out there. Here also the story is somewhat similar. We have electric field generated, which is sigma. Sigma is surface density of charge in the sheet upon 2 epsilon naught, and this electric field will give rise to field lines perpendicular to the plate, perpendicular to the sheet, straight lines perpendicular to the sheet, and parallel. Each straight line will be parallel to each other on both sides. Now we have electric field lines. Sorry, you have shifted to another. Yeah, please stick to this. We have field lines, electric field lines, as in the case of sonometer, we had struck, bowed, or plucked a string. Here, we are going to pluck lines of force. How could lines of force be plugged? Of course, they are intangible objects. They do exist, but not like string, some material form they are not. So what you do is you shake or move the sheet. So moving the sheet with, say, velocity, as I have shown, in a downward direction, will make the sheet, there will be a sheet of charge moving downward. So you are shaking this way the electric field lines which I have shown. No, not phonons. Phonon is quantum of lattice vibration. We are not going to that. We are sticking to very simple concept. The drawing analogy from, as I said, sonometer or stretched string. There we strike or pluck or bow a string. Here we are shaking electric field line, and by moving the sheet, say in the downward direction with velocity v. Please go to the next slide. Please go to the next slide, that is 19. So there will be, if v is the speed and y caret is the direction of unit vector in the y direction, the electric field perturbation will be v by c. V by c sigma 2 epsilon naught gives the dimension same as that of the electric field. So this perturbation delta E is such that it forces, the force it exerts on the charge of in the sheet will be resisting the motion of the sheet. Well, this is similar to one studied Lenz's law, for example, in the case of electromagnetic induction. The direction of induced EMF is such so as to oppose the very cause for which it is due. So the perturbation will generate a field, and that field will in turn resist the motion of the sheet. And suppose the sheet has area dA, so it contains charge dq equal sigma dA, and sheet is moving with velocity v, capital V I have assumed. So current created per unit length will be eta equal surface density of charge multiplied by velocity. And from Ampere's law, we know we have, whenever you have motion of charge constituting a current, there will be a magnetic field. So from Ampere's law, the perturbation in charge will also generate a magnetic field of the magnitude mu naught v sigma by 2. And if I now take ratio of d and dB, which has to be C, only when C is equal 1 upon square root of mu naught epsilon naught. I have not shown that explicitly, but I think taking the ratio and putting C as 1 upon square root of mu naught epsilon naught only will ensure that delta E upon delta B is equal C, well-known result. So one sees, therefore, that because C is the speed of electromagnetic wave, Therefore, one sees that indeed making a planar sheet, a planar charge move or, or shaking the electric field lines, one can create electromagnetic wave. This is the simplest way to generate electromagnetic disturbance. There are many other ways, and with this, I would like to end my lecture. Uh, 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 I have already sent a book of problems, uh, which is of course Sham series' book. So you have plethora of problems out there in the electromagnetics. So madam will ensure that each one of you gets that book. And other books that you have been referring to are, as our Professor Rachna Kumar showed you, that the book by Griffith, book by Jackson, lot many books are there, and of course this material will also be given to you. So I'm sure this particular portion will be, after you go through it, physics will be clear, as well as the calculation part, if you do yourself, will be clear. And as regards the problems, since Madam Rachna Kumar is doing the problems with you, so problems, if Dr. Punita says, I will touch upon, or if whatever. So with this, I thank you very much that you have patiently heard me out. And electromagnetics is really electromagnetic field theory is a very, very complicated field.
Yes.
Dr. Puneet.
Yes, sir. I'm very much here, very much here. Thank you so much, sir, for your nice lecture, and you have tried to give a new perspective to the students as to how they should deal with the subject. And over your lectures of classical dynamics also, any person who is going to listen carefully will be able to understand how to deal with the subject. All your PPTs of classical dynamics have been already forwarded to the students. Your problem set has been also given. So it's up to you. If you give some more problems for the CMT, they shall also be passed on to the students. We will have another. We will have 2 lectures by you also tomorrow, sir. So
Yeah.
So I think that should be more than enough. However, if they have any more queries, we shall be definitely passing them on to you. So
let me another important well, as a tail end to this discussion, internal reflection, external reflection, and the Brewster's law derivation needs to be done. That also comes in examination. And another important and slightly difficult is planar waveguide, another topic. So I would like to take up these topics.
Yes, definitely, sir, definitely. So along with my organizing team and my co-convener, thank you so much, sir, for this wonderful lecture. And we are really glad that you have agreed to take these lectures on EMT. And thank you so much. So tomorrow we'll have again lectures from you on this thing. And it's entirely up to you if you give more numericals, that we realize. And the students' attendance link is there. Kindly fill up your attendance, right? And tomorrow we'll be having electromagnetic theory by Dr. Partha, and we will have statistical mechanics lecture by Dr. Sanjay Kumar after sir's lecture. So with these words, thank you so much, sir.
Thank you, Dr. Goswami.
Welcome.
A lot for the very informative lecture.